Okay, so I mentioned templates, and templates are the way that we're going to get the settings and views and things that we want as defaults to show up each time. And if we find we're setting things more than once or twice, it's time to either add it to the template or create a template. So in the options and the document, templates typically we're looking for the parts in assembly or similar. What we get a departure is the drawings have a sheet format, and the document template is what shows up in the new. So drawings can associate the file properties of the parts in assembly to populate the title block. So we're going to build information into our parts in assembly, and then from the drawing point it back. So the views, the geometry in the drawing is not consumed by the drawing. It references the part in assembly. So when you send a drawing without the parts, it will come over with some information, but it loses, a lot of times it just goes to an empty box and says, oh, I can't find the part or the assembly, so too bad. Once that, sometimes the options stay active from session to session. Most of the time the system will stay active, but the document options, those kind of are hit and miss. Sometimes I pay attention enough to see that it didn't stay, and then other times I'm not quite sure. So the general statements for the drawing then are the sheet format holds the title block geometry and related properties. Then the drawing template holds the settings and the options, views, those types of things. And then they place the default sheet format files and the default document template files in separate locations. And I was going to look those up, so I need to add those to the mix. And so, nope, not ready for that one yet. So let's go through and we'll grab our default part. And I want to do a Control 7, which was isometric, which was the same as hitting the spacebar and clicking the isometric. I would like to see, now be careful, I don't think I mentioned this when we did the pull down. If you do that and click on the eye, it turns everything off, and we don't want that. So make sure that that's not grayed out, and then you will have access to the origins. I'll go ahead and turn the sketch relations on, but I will ultimately be turning those off. The blue origin is a good way to tell if you are in a sketch or not. So blue is you're ready to sketch, and red is you're in a sketch. What else would we like to see? Let's see, for the template, probably don't need anything in the configurations. I might add a work in progress. Really not doing the PhotoWorks. That is a carryover from previous. So if I delete, or I could just go ahead and make that my usually I have a work in progress or something that I can switch back and forth to. And then the other item that I might want is make sure that it's linked to the configurations. And for the work in progress, maybe not. So if I go just to the default display state, that will look more common, and maybe that one. We'll check one more time. So that's either on and off, and it's in all of them. So they either all link to the display state or none of them do. All right, so we'll come back to that later. For the view, I think my instant 3D is turned off, so that is on, and that is off. The instant 2D, we would want to make sure that that is off as well. And if you get orbits and things popping up that otherwise wouldn't want to see, then that's where they're coming from, is usually the instant 3D. So we had a few things in here that were already set, and I was going to check on the input, but I'm pretty sure that it's the modify box pops up and says, hey, what dimension when you place the dimension. You don't have to double click on the dimension to get that to pop up. We unchecked for the mark. If I wanted to change the color, and then I could go from blue to magenta. Because this is a system option that I'm setting, it probably is going to stay across sessions. I just want to check these. And display, box is the default. Yeah, file location. So let's get over to the document properties. So as far as a drafting standard, depending on what you selected when it installed, ISO or ANSI, and any changes that we make are going to cause this to go to a modified anyway. And then we can save to an external, load from an external if we want to use that same settings on multiple computers. So annotations, balloons, datums, geometric tolerances. These are going to show up in the parts and assemblies, but more so for the drawings. Our dimensions. If we do set for dual dimensions, we'll see the metric and the inch. Can be helpful at times, but probably more annoying. Virtual sharps are, say, places where the chamfer radius would come together, still more in the drawing. Tables, dim expert settings, detailing. Do we want to see cosmetic threads? I'm not real fond. Sometimes the shaded cosmetic threads look okay, but they've given me, well, probably been 10 years now that it gave me a problem, but I'm still, it doesn't add value for me. If you want to try them and leave them on, that's fine. Grids and snapping, same with the display grid. There are some strange things that go on with its functionality, and it doesn't really help. And if it tries to snap the display grid, it's still not helping. So our units, right now it's in millimeters. This is going to be a part for inch. And I will switch over to inches as my primary. And the dual length will go to millimeters. And that can be really 1 decimal place is 4 thousandths and 4 tenths. All right, so 2 decimal places for metric. Angles, lengths, how do you want to round? And so that should be good. Model displays, wireframes, again, more colors, more properties. The default material properties, but we're going to use the material over here more on the feature manager than anything else. Sheet metal, weldments, nothing really here. If you want to set colors, I don't necessarily pay attention to those. Interacting with the configuration. Oh, that's a good one. I'm not sure if that's in 2022. I'll have to check. Default bill of materials, part number. Most of the time, if I'm messing with those, I'm going to make a configuration name. Okay, so we do all of that. I've got most everything. If I come over here, do a quick check. Custom isn't listed, but if we go to the document units, that's going to take me back there. And then we do a file, save as, and we'll see if this puts me back where I was looking. So we're looking for a part template, PRT DOT. They used to have all of the Solidworks files up top, and then they just went alphabetical. So this is going to be my part inch. And to make a part metric, really all I'm doing is changing the documents and resaving this as a metric. So part inch. All right, we close that. We double check. Go into a new file. There's the template that I just created if I start with this one. And we come back and edit the document units. It was in millimeters first, so it was more for process than anything. And sometimes these stay, and sometimes they go, even though I've set it for 3 decimal places, it goes back to 2. So another one of those I need to figure out what I've told it to do. And we'll go back in, find our part template, Let's call this the part metric. All right, just to have something different from my previous. All right, so that gives me now two templates to work from that have things the way that I like them. Oh, no, I don't really. You do want to be careful with saving. Make sure that you change the folder that it's saving to. And it's kind of not an intentional mean trick, but the projects, the first 5 or 6 projects are in metric, and then the last couple are in inch. And I'm not sure how I did that, but well, there we go. All right, so we're going to hold off on the drawings. That will have to be a conversation. Drawings, for me, usually become a rabbit hole that once I go down, it becomes its own monster. The one I did in the end of 2018 or 2019, yeah, it took on a life of its own. So the design library are library features, reusable sketches, and features for the parts. And one of the things that I've used it for is sketches for text revisions that we would want to engrave on the part that are going to be reused or try to be consistent from part to part. The other item is I'll use stock sizes and targets for coordinate systems and those types of things. We have common components for the assembly in one place that can be referenced. It can be linked back to the original or made independent so that if there's changes, they update. The toolbox only works in the assembly, so when you activate the toolbox, you have the design library and then the toolbox. Right now the toolbox here is not active, but once it's activated, then you have the little down arrow, caret and the down arrow, that tell you what items are available, inch, metric, all of the different standards. And then we go to the hole wizards, which is a library of standard features, standard hole geometries. So once I go into a part and I go to look for the hole wizard, right now it's going to be grayed out because there's no geometry, so we have to create geometry. But under the hole wizard, we're also going to have threads and some other things that we can work with. So so things like counterbores, threaded holes, countersinks, pipe tapped holes. And they also have added slots, countersunk, say that 10 times, countersunk slots and counterboard slots. All right. So speaking of hole wizard, all of those numbers came from somewhere, and you will see a drill chart somewhere. If you don't have one, there are plenty on the internet. There are files, PDF files, and Excel files to reference from. So when we look at the drills for the inch, then we're talking about wire drills are number 97, the really small ones over here at 0.0059 or just under 6 thousandths. To 1, and number 1 is 228 thousandths. Fractionals by 1/64 go from 15 thousandths, and I want to say even at that rate, the 63/64, which changes size, a little bit of terminology on the drill geometry. Pretty much our fractionals will go from the 1/64 to ½ inch, and then so they stay at a ½ inch shank, they go to a silver dimming, which can then go up by sizes to 1 inch, or they are different tapered shank. I mean, there's so much geometry with the drills, and it just depends on the machine and the manufacturing process. So you're going to see different. Most everybody is familiar with the standard drill, and the geometry changes as it gets larger and does different things. So the letters then are A at 234 thousandths, to a Z at 413. So as you're looking through this, you're going to see the metric going by 0.1s, which if we when we go through the math is going to be about every 4 thousandths, so 67 to 71 to 75 as a rough number. And then when we talk about the size, the decimal inch for that size drill, and then the tap sizes that are used with that drill. And taps are pretty important because we're not going to put nuts and bolts. We're going to use screws, and that's really the only difference between a bolt and a screw is bolt goes with a nut, screw goes into the geometry. So when we're tapping that solid, that geometry, we're going to use a number 7, 201,000 for a 1/4-20 screw. So what does a 1/4-20 mean? So with the threads, we have machine screws that are 0 through 12, and fractionals are pick up at 1/4 inch and go all the way up to as big as you want to make. The metric screws found was 1.6, but there are smaller. Just like there is a double-aught and a triple-aught machine screw, there are smaller metric screws. All right, so it's kind of what is readily available. What can I open up a standard tap and drill set and pick out a tap and be ready to go. So our terminology nomenclature goes pitch is equal to 1 divided by the threads per inch. In metric, the second number is the pitch. No math needed. So our 0 to 12 machine thread, if we take a standard thread, the first number is the 0 through 12, and then the second number is the threads per inch. So to calculate a major diameter, you take that number times 13 and add 60 and then divide it by 1,000. The minor diameter then is the major diameter minus the pitch. So for the example, a 1032, we take the first number 10, major 10 times 13 is 130 plus 60 is 190 divided by 1,000 is 0.190 or 190 thousandths of an inch. The minor then is 190 thousandths minus 1 divided by 32, 0.03125 if you want to take it out that far, gets you to 0.159, and you go to the drill chart and find that it's a number 21, and we'll make the edit there. You find it's a number 21 drill, and then you pick that drill up. Depending on the material, it might go to a 161 or 164, but it's all about thread engagement at that point. Again, another conversation. I'm overwhelming you enough with all of these formulas and different drills. So to do the fractional major minor diameter, is the major diameter is the fractional or its decimal equivalent. So the minor diameter then still equals the major diameter minus the pitch, and we use a 1/4-20 or a 250 thousandths -20. Both of those are acceptable in our ASME standard. So the major diameter is 250. And the minor diameter is 250 minus 1 divided by 20, which would be 050 or 50 thousandths. And that equals 200, but since 200 is not on the drill chart, we don't really want to go down to 190 and increase the thread engagement. So we go up to a 201 or possibly a 204 or a number 7 drill. All right, so it's about making those selections, where those numbers for the whole wizard come from. There is a mechanical basis there. Metric threads being so complicated, the first number is the major diameter, and the second number is the pitch, so the major diameter is the M number. Minor diameter is the major diameter minus the pitch, so an M6 by 1. We have 6 millimeters for the major, 6 minus 1 is 5. So if it's an M5 by 0.8, I'm going to go find a 4.2. Well, I look at the index or the drill chart, and I find that a 4.2 is really close too, but if I don't have that drill chart and I'm not carrying around a machinery's handbook, I would like to be able to do a quick conversion. And that comes back to 1 meter equals 39.37 inches. And we can go out 6 decimal places, 5 decimal places, and say, I can pretty much, unless we're trying to calculate distances to planets, that 0.007 is not going to run into too much of an issue. So 1 millimeter is 39.37 divided by 1,000, 0.03937 equals approximately 40 thousandths of an inch. And that's only important for guesstimating, making quick estimates. All right, so if I round up, I get to 0.04. So 1 inch divided by 0.03937 is where we get the 25.4005, or 25.4 millimeters per inch. That was what I was taught in school, and I could not visualize 25.4 any things, but having been taught in the inch system, I know that 40 thousandths is between a 32nd and a 16th, and it's a pretty small number, and I can visualize, roughly I can visualize 40 thousandths. I can visualize a millimeter. So that being the case, if I take the 6 millimeters times the 0.03937, I get 236.2. And if I do 6 times 0.04, or 6 times 4 is 24, put the decimal place, I get 240. I'm within 4 thousandths. I'm within 0.1 millimeters, which is an acceptable error. And then 5 millimeters is 1997. You'll see it commonly referred to. So 5 times 0.04 times 5 times 4 is 20, and put the decimal place in front of it, I have 200 thousandths. All right, so quick numbers that they're just numbers. Be ready to engage and go back and forth, and and as those systems are probably not going away anytime soon, be prepared to work with it. So the thread forms, then we get into classes, fits, internals, externals. With metric, said that the 1.6 was the smallest my drill chart went, but notice it's way down here on the list, and it goes all the way down to a 0.25, which is a pretty small. It's about 10 thousandths on a with a 0.07. That is a really small screw. And then the class of fit is based on for the external or internal, and the fits I will refer to as the whole basis, commonly referred to as the whole basis, and the shaft basis. So a lot of times it's what is the purchase part and what are you manufacturing? What do you have control over as to which way you determine those fits? And then the class here is going to determine kind of the internal and external. So if I pick up a tap for an internal, I'll see this H value. And that determines the allowances, the clearances, and all the other fun things that you don't really want to know about right now, but are working in the background in the manufacture of these parts. So the inch, you'll have unified national, coarse, fine, extra fine, special decimal. And you'll see it in the, as we did before, the number, the threads per inch. Let me go ahead and update that. Doesn't make sense until I start talking about it. So, and then it will have a UNC, a UNF, a UNEF, or possibly a special decimal. The class is A for external, B for internal. So this is an internal thread. And the 2 is a standard thread. 1 is for dirty, kind of nasty environments where you want the loosest and still thread allowance and still have it go together. Standard, most common, and then you get to the tightest tolerance, which are going to be more, you can say generally the aerospace items. All right, now we get to actually sketching. So let's stop the video and then we'll do some sketching.